All right, let's continue our talk about geometry with the new section on similarity. So similarity is different than congruence. Remember, congruence means that the two figures are identical, whereas similarity means that the angles are congruent between the two figures, like the corresponding ones, but the lengths are not equal, but they're proportional. Proportional means that if you have, say, BC, and you have HI, and you have this one and this one, say this is 2 and this is 4. When we did dilations, we had scale factors, right? That's what's in play here. So say the scale factor is 3. So that means you multiply each side by 3 to get the length of the other side, as long as they're drawn in the corresponding way. So this would be 6 and this would be 8. No, not 8, 12. So that's what they mean by proportional. It means that each side is multiplied by the same thing to get the length of the other side. Okay, it's corresponding one. So an important part of this for me is to draw the figures just like this one, so we can clearly see, okay, top goes to top, bottom goes to bottom. A lot of times they'll give you the figures rotated and moved around in weird ways, so we're going to spend some time doing that. The symbol for similar is this guy. Okay, so it's like congruence, but just lose the equal sign because they're not equal anymore. So before I even start trying to answer, by the way, you could call this a similarity statement if you want, because they're not going to be congruent. They don't have the same sides. Anyways, so before I even try and figure out if they're similar, I think it's a good idea to maybe redraw one of them so all of the angles are in the same spots. Because right now we have the triple angle here. It's not, this one's on the left side, this one's on the right side. It's flipped around. So what I'm going to do, I think, is rotate this left triangle. I want to put my finger down on B and just spin it a little bit. So maybe if we, and I'll show you how to do this a few different ways, but I know that if I want this to be B, it better be the triple arc, and that goes with E. So B and E are now corresponding angles. Okay. The single arc is C, and the remaining double arc is B. Nope, sorry, A. Okay, and then since I know now, because that helps me a lot, because now I can see, all right, this side is gonna go, this one here might go with this one, and they might be proportional. And hopefully they're proportional, because they'd be similar if that's true. So between B and A is 12. Between B and C is 16, and the last side is 8. So I like this a lot because now I can breathe a little bit and see what's available. So angles, they correspond. Okay, that's clear to see. We were able to rotate it and line them up. Now we're going to see, let's take the little guy, the one that was on the left, and write down its side lengths. So 8, 12, 16. We're going to multiply that by something to get the other ones, 10, 15, and 20. Drawing the triangles so that they correspond like this and they're in the same orientation helps us write this in order, right? So the scale factor, which I want to call x, you can call it whatever you want. You can call it n, doesn't matter. You can just write scale factor. We hope that the scale factor from one side to the other is the same, okay? We want to multiply each side by the same thing to get the corresponding side, okay? So let's solve these equations. X is divided by 8, so that's 5 over 4. We're going to divide this one by 12 and get 5 over 4. and we're going to divide this one by 16 and get 5 over 4. Every side was scaled the same way. So yes, these are similar. And because we already drew the triangles in the same orientation, it's really easy for me to make sure that I write this statement correctly. So ABC is similar to, we start here and then go here and then go here. So we're going to start with D, go to E, go to F. Okay? All right. So let's see if these figures are the same. So I'm going to redraw the little home plate so I know which angles go with what. And it turns out that when I rotate it 180 degrees, the angles do match up. The diagonal ones were 6, and the vertical and the horizontal ones were 9. And since I've rotated it or reflected it 180 degrees, everything kind of spins around. So this will be R. Let's say I reflected it. So that's R and V. This is S and, well, hold on. Maybe we shouldn't reflect it. This is getting really particular, but when we reflect something, we change its orientation. So if it was top side up and you reflect it, it goes top side bottom. And I don't really want that to happen. So I'm going to do one of these where I take this and spin it this way. Like that. Again, don't worry if you do it another way. But I know that the corner here is T. And maybe, well, yeah. So it's up for debate, and it's going to be harder to visualize this as it's turning. But it's tricky because this shape is like symmetric, so it's kind of similar to more than one thing. So I'll just go ahead and reflect it like I was doing, because it does work for this case. Okay. Sorry, don't worry about that too much. I was just overthinking it a little bit, I think, for this case. So, and for what I want to show you. Angles match up, right? So that means they're on the way to being similar figures. But we got to make sure that the 6 goes with, it can be multiplied up to 12 in the same way that 9 can be multiplied up to 18. You see how there's only 2 numbers for side lengths? So we should make sure that those are scaled the same way. So 6 times something is 12, where this is the scale factor, and 9 times something is 18. So for both cases, we get a 2. So the scale factor from the smaller one to the bigger one is 2. So I think there's more than one correct answer for this, but if you want to say that A, so we would say yes, A, B, C, D, E, based on our drawing, should be S, R, V, W, T. And that is consistent with what I wrote in the answer key. But there's also more than one choice. For example, I think you could do S, V, U, V, R, S, T. Yeah. And that would also work. But don't worry too much about that. As long as you are showing me it's similar and matching up the shapes as they're given, it's fine. Okay. This one is a little interesting, right? They don't really look the same. But who knows? Maybe they are similar. How do we check? First, you look at the angles. Do the angles correspond? Like, could you go, hey, this one is this one, the next up, if we're going like a clock, is this one, then this one and this one, then this one and this one. Do they all match up? Yeah, they do. So the angles correspond. But maybe we aren't so convinced about the whole side thing. So if you go from JK, multiply it times something to get to TU, that would be 12 times something is 6. And we know that we're talking about a scale factor here. So x has to be 6 over 12, which is a half. But we also know that Jm goes to Tw. Right? So, but that's 6 times x is 6. And that means that x is 1. So the sides aren't scaled up the same way. So these are not similar. Okay, so there is no statement. All right, so this is a different question. It says, hey, these figures are similar. What could you tell me about x and y? Again, my preference, it's kind of hard to see the two triangles at first. But there's a little triangle with these sides, and there's a bigger triangle with these sides. And in fact, that's a Pythagorean triple. Okay, so that could help us, but we know that these are similar. So we know that their angles correspond, and we can kind of already see that. We have a red one marked, and we have this blue angle right here, which is actually shared between both of the triangles. And it's hard to see that unless you draw them separately outside the figure, for me. And we actually know that all the angles match up because this third angle, if you remember the third angle theorem we did a long time ago, if two of the angles of a triangle match up, the third one has to as well because they all add up to 180. Okay. So these are similar things, so I know, and because I drew the angles so that they're in corresponding positions, that x times the scale factor, I'll just write this, honestly. I normally use x for it, so I can't use that this time, but that's okay. So x times the scale factor is 8, and if we scale up y, so I'm looking at scaling the triangle so it gets bigger. So I expect my scale factor to be bigger than 1. Okay, so these are useful, but we can't find out what x and y are unless we have the scale factor. So maybe we need to take a look at this third side. That actually reveals it to us, because how do you go from 5 to 10? You multiply by 2. So the scale factor in both cases, since I know it's similar, is 2. So that means that x is 4 and y is 3. Okay. This way, the sides are all proportional. You multiply all the sides by 2 to get to the bigger triangle. Okay, so let's imagine we have a sheet of paper and we have this scale that says that 1 inch, maybe that's 1 inch, also is 150 feet. We're trying to draw a picture of this space needle. Okay, so he uses this scale, but we want to know if it's reasonable. And if we're making a picture, everything's probably pretty reasonable as long as it fits on the page. Okay, so I want to figure out if this scale factor of going from 1 inch to 50 feet, if that's reasonable, if the space needle is 605 feet tall. So you might see how to do this right away. You might not even think of doing it with this setup at all. you might say, hey, 1 inch is for 50 feet, and x inches of our drawing is this many feet. So it's a ratio. This is a ratio too. You might be more comfortable solving this one, which we just cross multiply since we have an equal sign. And when we divide, I got around 12.1. So what the 12.1 is it's the scale factor from 50 to get to 605. And whenever you scale to one side, you scale to the other side. So if this is 8.5 by 11, it looks like question mark, the height of our drawing, is going to go a little bit too tall. It's my Space Needle. And it won't fit on the page because 12.1 inches is too tall. So no. It extends off the page. And that's supported by our work. Okay. So we have three similarity postulates or theorems. And the first one is pretty basic. It says that if you have two angles that correspond, so the blue and the reds, if you see two angles that are identical, it actually means that the triangles are similar, right? And we could prove this based on what we know, but I'm not going to spend the time on it. I just want us to be able to do these problems. So let's try this. Let's see if we can find two angles that are the same within a triangle. And that's kind of it. If that works, then the triangles are going to be similar. So this is called the angle-angle similarity theorem or postulate. Okay, so you have to put this squiggle sign or else I'm not going to know what you're talking about, right? So especially when we move on to the next two, okay? So these are similarity theorems, right? They're not congruence theorems. They're not the ASA, SAS, AA, AAS, like there's none of that. It's similarity. We're trying to show that triangles are similar, not congruent. So we need that squiggle there. All right, so what could you tell me about this figure? Are these triangles similar? And we know vertical angles are similar, right? So that's two right there. We got two angles that are the same. This one goes with this one. This one goes with this one. So, yes. Triangle. Now, let's be careful here. So let's go RSW. RSW is similar to triangle. So angle R is 45. So we should make that line up with V. And S is loosely, S is the same as S, right? So S should be in the middle and then go to B. Okay? It's a different answer if you scramble those letters, right? This is the only correct answer. So make sure you're lining up angles. All right. And then these two guys, let's just go ahead and find out what the third angle is, right? 30 plus 70 plus what is 180? In fact, it's 80. So that's the third angle. And for the other one, 70 plus 85 plus question mark, the measure of angle P is 180. So it looks like that this is going to be 25. Now, between those two triangles, are there two that match? And you might say, yeah, 70s match, but you can tell that the others don't. So, no. no two angles are equal or congruent. Okay. So the next two, the other similarity theorems, this is it. They kind of come in a package because they kind of are saying the same thing. So it also works out that if you have side angle side between two triangles, they are similar. And if you have side 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 between two triangles, they are also similar. Now, how does this differ from SAS and SSS from before? It's a little different. You have to read this carefully, or else you might think they're the same. It's not the same old side angle side where it was like two sides are congruent and then an angle. It's proportional. So this means that they are proportional. So it doesn't mean that when we say S, we don't mean that the sides are congruent. We mean that they are proportional. Okay. Angles are still angles, right? So the angle, the A here still means angle, but the S's are saying that if you go, so this is like 10 and this is 20, then the scale factor is 2, so it would have to be the same for this side as well. So that meets the criteria for the SAS because this angle matches as well. So I would not say SAS because that's not true, right? They aren't congruent. But if you put a little this at the end, it means that they're proportional sides, and that's enough to show that the triangles are similar. So these are different theorems than before. So let's practice this then. So are these similar? Well, one thing I know is that these are not drawn the same way, and it's hard to see what matches with what. So it looks like, I'll pretend like this is a right angle to help me. It is, but we don't really know that yet. I'm going to draw a smaller right triangle over here, and I'm going to move my vertices. So T is this one. So I'm imagining kind of twisting or rotating this like this. Come on. Like rotating it like this, you see? So it actually turns out that if you watch U, it's going to go to W. Okay? And then this is 6, this one's 8, and this one's 10, because I'm just looking between two vertices. And I know that 8 is between S and is between U and T. So this helps me a ton, because now I know what sides match, and maybe this can help. This has nothing to do with angles. You see, none of the angles were labeled. So out of our 3 theorems, I think this might be SSS similarity. So let's see if it's true that all 3 sides are proportional. So I'm just lining these up. I'm going, so like for this last one, for example, I said 15 goes to 10 when I multiply by this scale factor. Okay, so each of these I can solve for x. They're pretty easy equations. 6 over 9, 8 over 12, and 10 over 15. But I'm not quite sure if these are the same fraction, right? So simplify, simplify, simplify. Haha, they are. They're all proportional. So all sides are proportional. And in a triangle, normally that's not enough for similarity, right? We need angles and sides that are proportional. So the triangles are similar by SSS similarity. And yeah, we aren't proving those things, but it's important to see that. Okay? So we can see sides, not congruent, but they're proportional. And that's enough for similarity. Okay. I think they want the congruence statement as well. So this is the scale factor, SF, whatever you want to call it. And it's much easier to write these triangle similarity statements or congruence statements when all the triangles are oriented the right way. So I'm going to start with X, go up to V, go over to W. So down S, up to T, over to U. All right. Let's take a look at this next one. So, again, two triangles inside of themselves. It might be a little bit more complicated to leave the figure like that. I like to draw the figure so I can really see the two at once. So this is a little one, so it's 8 and 12. The big one extends by 2, so this will be a 10, and this will be a 15. And when you have triangles nested in each other, they share an angle. So this angle matches with this angle. And I don't really know what the third side is right now, but the thing is we might not need it because our choices for similarity to prove similarity are these three. And I only have one angle. I don't have any sides. I'm sorry. I didn't mean to say that. I only have one angle, and I don't have any more, and I only have two sides. So I'm thinking this one makes the most sense because I do have two sides that could be proportional, and I have an angle between them. So that will work. And that angle is between the two sides, so it is SAS. So if I want to show similarity, I need to show proportional sides. So does 8, can we multiply 8 by something to get 10? And in the same way, multiply 12 by something to get 15. And if I divide and divide to solve for x, I find out that both of them are 5/4, which is great. So two sides are proportional, and its included angle, remember included means between, is congruent. So we truly do have SAS similarity. We don't have equal sides. They're only proportional. So we know that this KPL, KNM are similar by SAS similarity. And this is the scale factor. Okay. Two more questions. I know it's a longer video. We're going to do more practice with this too throughout the week. So let's say we have a child here who's pretty tall, standing next to a flagpole. Okay. So the child's shadow, I'm also looking at the shadow of a flagpole. So if the sun is casting a shadow like this, the child's shadow is here, and the flag's shadow is here. You see? It's telling us that this length is 7.5, and the child's shadow is 1.2. Okay. How tall is the flagpole? So we'll call this maybe Y, vertical distance. And then we have the height of the kid as well. So that's great. Great picture. Maybe we need to simplify it a little bit. So 7.5 and this is y. Okay. Well, one thing that we know is that we have similar triangles. Okay. Why do we know we have similar triangles? Well, let's take a look at these triangles. Well, if you really want to know why we have similar triangles, and I'll erase this in a second, but if you have a figure like this, you have an angle here, and because these two things stand up straight, you have parallel lines. How about that? So these correspond, and so do these. So you got two triangles, and you have more than enough for angle-angle similarity. Okay? So we know these triangles are similar, which is an important part of the discussion. But let's take a look and see if we can draw each of these separately, at least for one time. I think I would maybe set up a fraction. So I know that the vertical segment is some proportion with this, and it has to be the same proportion of when I take the small bottom to the big bottom. It's basically saying, hey, this goes to this goes to this, and I know those ratios are the same because they're similar. So what you can do is solve this guy. So it should be, hold on, let me just calculate this for us real quick. So we'll cross multiply. So I get 10.5, which means that y, if we divide that by 1.2, we get 8.75 meters. Remember that meters is important here in the discussion. Okay, but they are similar triangles by AA. Again, this angle matches, and so does this angle, because they're parallel. So we definitely have two angles that match here. All right, and then finally, given the two triangles are similar, solve for x. Again, it's kind of freaking me out a little bit that they're not all the same. So I want to put short leg here and the right angle. So the long leg looks to be 24. Short leg does not have a label. Again, this is empty. And we have this. Okay. So just like we just did in the other similar triangle problem, we know that we can set up a ratio or a proportion. So 24 is to 2x minus 4, just as x plus 6 is to 39. Okay, and this is definitely more of a challenge, but I thought we would do it together rather than me slam one on the homework. The homework question's easier. We gotta do a lot of steps, don't we? We gotta cross multiply here. So this would be 936, and we would be multiplying like that. Okay? In order to solve for x, this is a factoring question. We gotta set it equal to 0, if you remember that. So what's gonna happen is, this is the next step. Let's slow it down a little bit. I'm going to first times first, outers, inners, and lasts. There. That's the missing step I didn't include. And you get that, and then now you have to factor. But this 2 makes factoring a lot harder, but everyone's got a 2. So we can divide by 2 and get this. And 480 is ridiculous for me to ask of you, but this is what the problem was. But remember, you can do this, and for this to turn out negative, it has to be minus plus, and I just want to give this to you, is 20 and 24. So x is 20 and x is minus 24. But this doesn't make any sense when we're dealing with lengths, especially since one of the sides is x plus 6. So there you have it. Okay, so that was the answer. Tricky one. We had to pull back factoring, but it's good to take a look at that. Okay. All right, that's it. Try out the homework here. We might end up working on this over 2 class periods.